Solids of revolution, the washer method. Take a moment to imagine revolving this shaded region around the x-axis. What would this three-dimensional solid look like? So we're talking about this region here in quadrant 1, bounded on the x-axis between a and b, and between these two functions f of x and g of x. So notice that this time the region is not right up against the axis of rotation. It's not right up against the x-axis. So we have this gap happening. So try to imagine what rotating this around the x-axis would look like. This figure is a bit trickier than our previous solids. Notice that the shape of the cross-section is a washer. So we're thinking about the tool, the piece of hardware, a washer, because of that gap. So if I focus on one particular x value between a and b, at that x value, if I think about this lined segment here that's drawn between the point A and the point B, if I think about taking that and rotating around the x-axis, the cross-section that is formed is that piece of hardware, a washer, right? And so this integration process is going to have us add up the area at each x value between a and b to form the volume. So the solid has this big hole in the middle of it, right? So if we look at it from the sideways perspective, we have that circle within a circle. So what we're going to need is two radii. So we're going to need to find the area of the outer circle using the big radius minus the area of the inner circle using that small radius. And then we're going to use that integration process to add up all of those areas to find the volume of the solid. Let's take a moment to formalize the formula for finding the volume of a solid of revolution using the washer method, where the cross sections are perpendicular to the x-axis. So the washers are stacked vertically, extending from x equals a to x equals b. What we need is two functions, f of x and g of x, that are continuous, and f of x is greater than or equal to g of x, and both of them are positive. So f of x is above g of x, and both are above the x-axis on the interval from a to b. Then the volume obtained by revolving this region between the graphs about that x-axis is going to be found by doing the integral from a to b of pi times the big radius squared dx. So the big radius here extends from the axis of revolution all the way to that farthest away function here, f of x. And so if we find this first integral, that's using the disk method. So we're finding the volume of this solid that doesn't have a hole in it, but now we have to carve out that hole. So we have to subtract this other integral, the integral from a to b of pi times that smaller radius squared dx. So that smaller radius here, the radius extends from the x-axis to that closer function, g of x, that's the smaller radius. So we're going to find the volume of that solid and carve it out, which is why we're subtracting it. So it's doing two separate integrals, but because we have the same limits of integration on each, we can actually combine it together. So the big radius I'm calling capital R of x, the small radius lowercase r of x. They both have a pi, which is a constant multiplied in the integrand. So I pulled out the pi, and again, because they're the same limits of integration, we can combine the integrand to be capital R of x squared minus lowercase r of x squared. So this is sort of the really general formula that we can use, and then our goal is going to be to find capital R of x and lowercase r of x. What's that big radius and what's that small radius? And if we're rotating around a horizontal line like the x-axis, we can think about finding each of those as a top minus bottom situation, top function minus bottom function. So for this problem, the top function up there is f of x. So f of x minus 0, the x-axis is 0, so we have f of x squared. And then the smaller radius, top minus bottom, is g of x minus 0. So the formula for here, this setup, is pi times the integral from x equals a to x equals b of f of x all squared minus the quantity g of x squared dx. So again, capital R of x is that outer, that bigger radius of the circular cross-section, and lowercase r of x is the inner or smaller radius of the circular cross-section at different values of x. Let's look at an example. We want to find the volume of the region found by revolving the area in the first quadrant, bounded by y equals the square root of the quantity 4 minus x squared, y equals x, and the y-axis around the x-axis. We need to start by finding this area that we are rotating. So let's graph the square root of quantity 4 minus x squared, which is a semicircle on top of the x-axis with a radius of 2, the line y equals x, and then the y-axis. Here are my graphs, and the region that's bounded by all three functions is going to look a little bit like a pizza slice or a pie slice here. So we're bounded in quadrant 1, and we're bounded by the y-axis, y equals x, which is just a line passing through the origin with a slope of 1, and then that semicircle on top of the x-axis with a radius of 2. All right, so we are going to be rotating this around the x-axis here. So how do we know that we have a washer method as opposed to a disk method? So if there's any type of gap, if there's any gap at all between the region and the axis of rotation, then we're going to have a washer method situation. So that's why it's important to draw the region very precisely and highlight the region so that we can see if there is this gap between the region and the axis of rotation. And so let's go ahead and get started. So we're going to have the volume is, I'm going to leave the pi on the outside, pi times the integral from x equals 0. So 0 is that x value that we are starting at, but we actually don't know the other limit of integration because we need this point of intersection here. So I'm just going to leave it as x equals for a moment. And then what we're going to need is that big radius squared and the little radius squared. So I like to think about that again as going from the axis of rotation to that sort of farthest away function there and thinking that's my big radius, right? So that's going to form its own solid when rotating that doesn't have something carved out of it yet. And then I have to figure out, well, what's that part I have to carve out? So I start from that axis of revolution and I think about what's that closer function. So that's going to be here. Whoops. So that's going to be here. This is going to be my little radius. This is going to be my little r. So I need that big radius squared minus the little radius squared. That's how I like to think about it. So my big radius, top minus bottom, is the square root of 4 minus x squared minus 0, because the bottom of that big radius is the x-axis, and that is just 0. So all of that gets squared, minus the little radius. And so the little radius there is top minus bottom, so the top is x. So we have x minus 0, which is just x squared. So all of that dx. So the only thing that we're missing is the other limit of integration, which we find by setting those two functions equal to each other. So we're going to do sort of that scratch work where we solve 4 minus x squared is equal to x. We'll square both sides. 4 minus x squared is equal to x squared once I square both sides and eliminate the square root. I have 4 equals 2x squared. Once I add the x squared to the other side, if I divide by 2, I get 2 equals x squared. And then solving for x, I'm going to get plus or minus the square root of 2. So there's two solutions because there is another place where if this circle was completed, if I had the entire circle instead of the semicircle, the line would intersect again down here. But we're only thinking about quadrant 1 right now, so we just need positive the square root of 2 as our other limit of integration. And so that is the setup now to finish, to get a numerical value for this volume. I'm going to simplify the integrand so I can take the first part and get rid of the square root because of the squared that's happening here. So I have pi times the integral from 0 to rad 2 of 4 minus x squared and then minus x squared dx. So pi times the integral from 0 to rad 2 of 4 minus 2x squared dx. So not too bad to integrate here. We're looking at 4x minus 2x cubed over 3 evaluated from 0 to the square root of 2. Now thankfully on this problem, plugging in 0 into each of these terms, we'll just get rid of those terms. So we're really just thinking about plugging in the square root of 2. So I have pi times 4 rad 2 minus 2 rad 2 cubed over 3. That's going to be pi 4 rad 2, and then what's happening here, if I square the square root of 2, that's going to give me a 2 to pop out to multiply to this 2, and so one copy of rad 2 is going to be left there because there's 3. I'm multiplying it by itself 3 times, so multiplying it by itself twice will give me a 2, so this is going to be 4 rad 2, so minus 4 rad 2 over 3. And so if I make common denominators, multiply the bottom by 3, that would make this a 12. So we're looking at 12 rad 2 minus 4 rad 2 over 3, that's 8 rad 2 over 3. So 8 rad 2 over 3 pi. 8 rad 2 over 3 pi is my volume. So note, it is possible to revolve a region about a horizontal or vertical line other than the x-axis or let's say the y-axis, right? So the horizontal or vertical line we revolve a region about is called the axis of rotation, or sometimes it's called the axis of revolution. So just formalizing that, I have said that out loud already, but that line that we rotate around can be either the x or y axis or really any horizontal or vertical line. Let's look at another example. This time we're just going to set up the integrals needed to find the volume V of the solid generated by revolving the regions bounded by y equals x and y equals x squared about the line y equals 2. Let's start by drawing our functions. We have y equals x. That's just, again, the line passing through the origin with a slope of 1. So let's see. We have y equals x. And then y equals x squared, that's just that parabola, also passing through the origin. And the point 1, 1 and the point 2, 4, that's going to be off the graph here. But I'm going to make sure and sketch this as a parabola here. And so it does continue to the other side, but we want the region bounded between these two functions, which is just this little sliver here that's in quadrant 1. And we can see that these intersect at 0, the origin, and at that x value 1. So by drawing a detailed graph, we found those points of intersection. We were able to. And so we are rotating this time around a different line, not the x or y axis. So we're rotating around the line y equals 2. So here y equals 2 is a horizontal line, and it happens to be above the region that we're rotating, but that's okay. We can still do that. So we want to identify whether we're going to be using the disk or washer method here. And so since we've clearly shaded the region that we're rotating, and it's not right up against the axis of rotation, in fact there's a huge gap here, this is going to be a washer method. So we're going to have this big radius and this small radius involved. So let's get started with our setup. We have volume is equal to, pi, put the pi in the front, pi times the integral from x equals 0 to x equals 1. Since these washers are going to be stacked vertically, we're going to be integrating everything with respect to x. So we're extending from x equals 0 to x equals 1. And we need that big radius and that little radius so that we could take each one and square them and subtract. So I like to start by going to that axis of rotation or axis of revolution and going to the farthest away function, because that's going to give us the biggest radius, right? So from the axis of rotation to the function that's farthest away, that's going to be my big R, right? So to find that big radius, we're going to do top minus bottom. So we're going to do, in this case, 2, and then minus, well, what's that bottom function there? A really good habit to sort of start is to label the equation close to the graph, right? So that you can kind of easily identify it. So we have 2 minus x squared is my big radius, and then my little radius. So from the axis of rotation to that closer function involved in the region that we're rotating, that's going to be my little r. And so the top of that little radius is 2, and the bottom of that is going to be x, because this line here is y equals x. So it's going to be 2 minus x. So that's my big radius and my small radius, right, across the entire interval from 0 to 1. The bigger radius and the smaller radius are going to stay the same. So when we set this up over here, I'm going to have the quantity 2 minus x squared minus the quantity 2 minus x squared. So that's my big R squared minus my little r squared. And we're integrating with respect to x. Now there is a part B to this problem where we're still going to take that same region bounded between y equals x and y equals x squared, but this time we're going to set up an integral to rotate around the line y equals -1. And so y equals -1 is a horizontal line, but it is below the region that we are rotating. So what we're going to do to start to set this up is we're going to have that the volume is equal to pi times the integral from x equals 0 to x equals 1 again. So the limits of integration are determined by the region that you're rotating, right? And they're x values because our cross sections are perpendicular to the x-axis, right? We're envisioning adding up from x equals 0 to x equals 1, all of these quote-unquote areas, right? These really skinny slices, these areas, and we're adding them all up from 0 to 1. And so we just need to find the area of that outer disk and then minus the area of the inner disk, because that's going to carve out that inside. So to find the big radius, we start from the axis of rotation, which is again below the region this time, and we go to the furthest away function, and we call that capital R. All right, so the furthest away function in the region this time is x. So the radius, we're going to always find doing top minus bottom. And so that's going to give us x minus -1. So x minus -1 is going to give us an x plus 1. And then to find the smaller radius, we start from the axis of rotation. We go to the closer function for the region, and that's going to be x squared. So little r, right, the little radius that we're going to carve out, is top minus bottom, so we have x squared minus -1 again. So x squared plus 1. Right, so we're always going to do that top minus bottom because, you know, we're thinking about how these represent numbers. So we're going to take the positive value, right, and subtract the negative value to find that distance. So if we wanted to find the distance between 2 and -1, so I'm just putting specific numerical values on this, right? So 2 to -1 is a distance of 3, but we would find that by doing 2 minus -1, and that's going to give us 2 plus 1, which is 3. Right, so that's why we're kind of always doing that top minus bottom situation when we have a vertical line to find the distance, right? That's what we're trying to do, is find distance. So let's set this up. We have the big radius, that was x plus 1 squared, minus the little radius squared, that was x squared plus 1 squared. And we're integrating with respect to x, so that's my big R, and that's my little r. In this example, we want to set up the integrals needed to find the volume V of the solid obtained by revolving the region bounded between x equals 4 minus y squared and the y-axis in part A about the line x equals -2. And you'll notice that here we have the volume formula as a function of y. So let's go ahead and sketch our region. So 4 minus y squared is going to be a parabola that opens to the left. So since this is y squared, it's either going to open right or left, and the negative means it's going to open to the left. And 4 is going to be the x-intercept. So if I let y equal 0, then x is equal to 4. So let's go ahead and graph this parabola. And so notice that the y-intercepts are at 2 and -2. If I think about setting this equal to 0, 4 minus y squared, I'm going to end up getting plus or minus 2. And then the y-axis, so let's draw that. And then we'll highlight the region between. All right, so now we want to rotate this about the line x equals -2, which is a vertical line. So here it is, and our region is clearly not right up against the axis of rotation, so we are going to need to use a washer method. So if I start from the axis of rotation and I go to the furthest away function, that's going to give me my big R. And then if I start from the axis of rotation and go to the closer function, that's going to give me my little r. And then I find each of those radii by doing right minus left, since these are horizontal lines. So we find those distances by doing the right side minus the left side as functions of y. So we're integrating here. If we were to draw a sample of the cross-section, we'll just show the sample cross-section down here. We know that they're stacking up along the y-axis. So our limits of integration are going to be y values. So we're going to have v is equal to pi times the integral from y equals -2 to y equals +2 of the big radius squared, which is the right function, x equals 4 minus y squared, minus the left function, -2. So we have 4 minus y squared minus -2, all squared, minus the little radius squared. So this little radius, I mean, it's always a distance of 2. So we can do it formally and say right minus left, because that's 0 minus -2. But we don't have to. We can just understand that that inner radius that's carved out at every single y value is just 2. And then dy. So let's clean it up a little bit. We have pi, the integral of -2 to 2 of inside here. This minus the negative is plus, so that's a +2, and there's a 4 in there. So 6 minus y squared, all of that squared, that's big radius squared, minus the little radius squared, 2 squared dy. And I can actually use symmetry here. So I can see that if I double the integral from 0 to 2, that I'm going to get that half of the volume, so then I can just double it to get the full one. So if I was actually evaluating this, so I'm going to put another option, or I can say that the volume is pi, 2 pi, excuse me, we're going to double it, 2 pi, the integral from 0 to 2 of the same integrand, 6 minus y squared squared minus that 2 squared, I'll write it as 4 dy. So that's another choice. I just have to remember to double it. Now here we have the exact same region, but this time we're rotating about the line x equals 6. So x equals 6 is a vertical line, but this time on the right side of the region. This time we still have a big gap between the axis of rotation and the region, so we are going to need a washer method. So if we start from the axis of rotation to find the bigger radius, I'm going to go to that further away function, which this time is the y-axis, and that's across the whole region. So there's my big radius over all of -2 to 2, and then my smaller radius from the axis of rotation to the closer function this time now touches that parabola. And so we're going to go ahead and still set up our limits of integration from -2 to 2, at least originally. So we'll have that volume is pi times the integral. These are y values, -2 to 2. And then we have our big radius, which this time is 6. So that's the right side, 6 minus 0, or just 6. So 6 squared. And then the smaller radius is going to be the right side 6 minus the parabola, and the parabola was 4 minus y squared. So we have to be careful and keep that binomial in parentheses because this is going to distribute dy. So let's simplify this a little bit or clean it up. So we have -2 to 2. Let's write it as 36 minus 2 plus y squared dy. So remembering to distribute, and then 6 minus 4 is 2, and then the negatives become a positive. And for the same reason as the previous one, we have the option to set up the volume as 2 pi using symmetry, the integral from 0 to 2 of the same integrand, 36 minus 2 plus y squared dy. Here, let's set up the integrals needed to find the volume of the solid obtained by revolving the region between y equals 9 minus x squared and y equals 12 on the interval from 0 to 3 about, in part A, the line y equals 12. So let's sketch the region. 9 minus y squared is a downward facing parabola with a y-intercept of 9 and an x-intercept of 3. Hopefully we can see setting this equal to 0. We'll get plus or minus 3, and we only want this on the interval from 0 to 3. And we have the equation y equals 12, which is a horizontal line, but we only want it on the interval from 0 to 3. So here's that horizontal line, and we're talking about the area trapped here. All right, so we want to rotate it around the line y equals 12. So that's actually this same line right here. And if I rotate it, I notice that there is no gap between the region and the axis of rotation. So it's only going to need a disk method. There is only one big radius here, r. And we'll go ahead and start to set up the volume. We have pi times the integral from x equals 0 to x equals 3. So we are stacking these up vertically. Let's sketch one sample cross-section. So they're stacking like this. So again, we're adding things up along the x-axis. So we have x equals, x equals 0 to x equals 3. And then just a big radius, and the big radius is top minus bottom. So the top function was that y equals 12, and the bottom function is 9 minus x squared. So we have 12 minus 9 minus x squared dx. So we have pi, the integral from 0 to 3, and then simplified inside, I'm going to have 3 plus x squared dx as my setup. Now in part B, we want to rotate around the line y equals 15, which is still horizontal, but now above the region. And there is a gap between the axis of rotation and the region, so we're going to need the washer method. And so I'm going to start from the axis of rotation, and I'm going to find the big radius by going to that farthest away function. It's always the same, It's always the parabola, so I have my big R, and then from the axis of rotation to the closer function, I have my little radius, and we find both of these doing a top minus bottom. We're still integrating from 0 to 3, so I'll have pi, the integral from 0 to 3, these x values. And then my big radius is the top function, which is that y equals 15. And then the bottom function is the 9 minus x squared. So we have 15 minus the quantity 9 minus x squared, all of that squared, minus my little radius. Well, my little radius is really always just 3. So we can do top minus bottom, but we can see that the inner part that we're going to carve out always just has a radius of 3. So I'm just going to go ahead and put 3 squared and then dx. And we'll simplify it a little bit. We'll say 0 to 3, 15 minus 9, that's 6, plus x squared squared minus 9 dx. And now we're going to take the same region and rotate it about the line x equals -1. So x equals -1 is a vertical line. So we're mixing it up on this last part here. And if we rotate around this line, if I think about, there is a gap between the axis of rotation and the region. And if I start at the axis of rotation and I go to the function that is furthest away, that is always going to be the vertical line 3. It doesn't matter where I'm at. So if I'm up here, the furthest away function is 3. And if I'm down here, the furthest away function is still 3. So my big R is constant over the entire collection of y values here. So we are going to be integrating with respect to y because these are stacking up. My washers are going to stack up vertically. But my inner radius is going to change. So if I were to pick the axis of rotation location here at this y value and then try to find the small radius, that's going to be now touching the parabola if I'm down here. And so that's a little r. But if I were to happen to choose the axis of rotation up here and then go to the closer function, now I'm touching the y-axis. That's little r. So basically, we have to split this up into two integrals. So I'm going to say there's a little r1 and a big R1 between 0 and 9. But between 9 and 12, there's a little r2 and a big R2. So let's go ahead and set up the two integrals we would need to find the volume if I rotate around this line x equals -1 using the washer method. So we have the volume is pi, the integral from y equals 0 to y equals 9 of my big radius 1. So I'm on this bottom part here. So that's 3 minus -1. So I'm going to have 3 minus -1 squared minus my little radius 1, which is right minus left. But hold on, our function is given as a function of x, and we have y variables. So if I have y equals 9 minus x squared, I have to solve for x. So then x squared equals 9 minus y. So x is plus or minus radical 9 minus y. So this is on the positive side. So this equation is positive radical 9 minus y. And so that's what I want to use when I do right minus left. So it's going to be radical 9 minus y minus -1 squared dy. Ooh, okay. So I have done the volume rotating between 0 and 9 around this line y equals -1. But now I have to rotate the portion between 9 and 12. So we're going to say plus pi, the integral from y equals 9 to y equals 12. Same big radius. So we're still going to have 3 minus -1 or 4. So I'm going to put 4 squared minus, this time, this little r2, I feel like this looks like square root of 2. Sorry about that. I'm going to fix it. So it should look like a r sub 2. So this is always just 1. So 0 minus -1 is just 1. So I'm going to go ahead and put 1 squared dy. And so I'll clean it up a little bit. So we have pi, the integral from 0 to 9 of 4 squared minus radical 9 minus y plus 1 squared dy plus pi, the integral from 9 to 12 of, I can actually simplify this further, right? It's just 16 minus 1, so we're integrating 15 dy.